In this example, we're going to find the parametric equations for the line of intersection between the planes defined by the following equations. The first plane has the equation 3x minus y plus 2z equals 1, and the second plane has the equation 2x plus 3y minus z equals 4. Since these two planes were given that they intersect, we know that they are going to intersect along a line. Let's illustrate this qualitatively. Let's say this is one plane with a normal vector given by n1 vector. And let's say we have another plane off at some angle. This plane has a different normal vector, n2. These two planes intersect along this line of intersection. We now have to find an equation of this line of intersection, and specifically a parametric set of equations to describe this line of intersection. You may remember from a previous lecture that we could describe a parametric set of equations for a line in space given as some position vector r for a point on the line is equal to some known point on the line plus a vector that is parallel to the line times a parameter t. This is our equation of a line in three-dimensional space, where v is a vector that is parallel to the line. Let's go ahead and give this vector components a, b, and c for the x, y, and z components of the vector respectively. In this sketch of a plane that I drew, that vector v may look like this. Here, I'll fatten this up a little bit. We could call that vector v. And a point in this plane, well, let's just go ahead and pick the tail of that vector I drew as our point. So this point right here will correspond to r naught, and r naught is the position vector that has components x naught, y naught, and z naught when we draw the position vector starting from the origin to that point in an x, y, z rectangular coordinate system. R naught then is x naught, y naught, and z naught, and any point along the line is given by position vector r with coordinates x, y, and z. Therefore, we could have a parametric set of equations with these vectors given as x equals x naught plus at for the x coordinate, y is equal to y naught plus bt, and z is equal to z naught plus ct. Well, in order to determine this parametric set of equations, we are going to need a vector v that is parallel to this line of intersection, and we are going to need a point in the plane given by the position vector r naught, or located by the position vector r naught. So how do you think you could find a vector that is parallel to this line of intersection given the two planes? Think about that for a moment. Well, let's look at those two normal vectors. We had a normal vector n1 roughly going off in that direction, and let's refer back to the picture. We had another normal vector n2 roughly going off in this direction, and we have the line of intersection given by the intersection of those two planes roughly going off in that direction. And here's the thing. These normal vectors are each perpendicular to that line. Since both normal vectors are perpendicular to that line of intersection, what if we evaluated the cross product between the two? Remember, the cross product between two vectors yields a third vector that's perpendicular to the first two vectors. So if we take the cross product of n1, cross it with n2, that is going to give us a vector in the direction of vector v. And we don't have to call it a unit vector. So let's just go ahead and say n1 cross n2 will be our vector v, because v is perpendicular to both vectors n1 and n2. Well, let's evaluate that cross product. n1 cross n2, I am going to evaluate this using a 5x3 matrix where the columns correspond to the different x, y, and z components, and the rows correspond to the two different vectors and the unit vectors in the top row. The second row has the components of the normal vector for our first plane. The components of the normal vector for our first plane is 3 minus 1, 2, and then I will repeat 3 minus 1. The third row is formed from the components of the normal vector of our second plane, which has components 2, 3, minus 1, and let's repeat 2 and 3. This is our 5x3 matrix. To evaluate this 5x3 matrix, I am going to take the products along one diagonal and subtract the products along the other diagonal. In doing that, we have a vector where the x component is given by the product of minus 1 times minus 1, and that is minus the product of 2 times 3. If you're wondering where I got that from, I got it from looking at these diagonals, taking the diagonals down and to the right and subtracting the diagonal down and to the left for the x component. The y component is similar. I'm going to take the product of 2 and 2 and subtract the product of 3 and minus 1. For the z component, I'm going to take the product 3 and 3 and subtract the product minus 1 and 2. This means that our cross product has a component where the x component is 1 minus 6, the y component is 4 plus 3, the z component is 9 plus 2. Therefore, our vector that is parallel to the line of intersection given by the cross product of the two normal vectors has components minus 5, 7, 11. This means that A corresponds to the x component of this vector, B corresponds to the y component of this vector, and C corresponds to the z component of this vector. Well, now that we have found a vector parallel to the plane, we now have to find a point that lies in our plane. And not just in one plane. Because this is a line of intersection that is shared by both planes, the point that we have to find must be a point contained by both planes. So how do you think we should do that? Let's copy our sketch of the planes to a new page. Here are our planes. We have to find a point on the line that's shared by both planes. So let's say these planes sit in an x, y, z coordinate system. What if we looked at a point on the zy plane, for example? So let's look at the zy plane. And let's take the zy plane and look at where it intersects our planes. That intersection might occur right here. That coordinate right there along that line is the coordinate x equals 0 that is shared by both planes. Let's do this. Let's look at the point x equals 0 for both planes. And that point x equals 0, let's use that and plug it into our parametric equation of the line for both planes. Let's look at our point x equals 0 along that line. That point x equals 0 is also going to lie in both planes and shared by both planes. Since x equals 0 is shared by both planes, let's return to the equations of the planes. We have 3x minus y plus 2z equals 1, and we have 2x plus 3y minus z is equal to 4. We are saying let's look at x equals 0. So in looking at x equals 0, these terms will go away. Now we could have chosen y equals 0 or z equals 0 and canceled those respective terms out. It's really kind of arbitrary, me choosing x equals 0, but we could have chosen the other two coordinates as well. Well, in looking at this, and in adding these two equations, well, we could do something with these two equations. And let me just rewrite them down here for clarity. I have minus y plus 2z equals 1, and then we have 3y minus z is equal to 4. Let's do this one. What if we multiply the second equation by 2? In multiplying that second equation by 2, I'm going to go ahead and rewrite each equation, but the second equation is now multiplied by 2, so we have 6y minus 2z is equal to 8. And now look at what we have. We can just add these two equations, giving us 5y is equal to 9, or y equals 9/5. So now we have a value for x. X equals 0 is a point on the line. We have a value of y. Y equals 9/5. Now that we have a value for x and for y, let's find a value of z. And once we get a value of z, that's going to be our point in our plane. So to do that, we can use either equation. And actually, we're going to use both equations so we could check ourselves. So let's start off with the equation for the first plane. Equation of the first plane, we have x equals 0. We have y equals 9/5 plus 2z is equal to 1. 2z is equal to 1 plus 9/5. 2z, if I'm doing my algebra correctly, is equal to 14/5, or z is equal to 7/5. Okay, we have x equals 0, we have y equals 9/5, we have z equals 7/5. Let's plug these points into our second plane's equation to see if we get an identity. The left side should be equal to 4. And if it is, then we've correctly done our work. We've checked ourselves. So I'm going to plug in the points that we have into the second equation of the plane. That equation again is 2x plus 3y minus z is equal to 4. Plugging x equals 0 in, plugging y equals 9/5 in, and plugging z equals 7/5 in, that is equal to 4. Well, 3 times 9 is 27 divided by 5 minus 7 over 5 should be equal to 4. We get 20 over 5 equals 4. We get 4 equals 4. It checks. Because it checks, we now have a point in our plane. We will call this point P0, or not a point in the plane, a point on the line of intersection that is shared between the line and both planes. And that point has an x-coordinate of 0. The y-coordinate, let's see what the y-coordinate was. The y-coordinate was 9/5, and the z-coordinate is 7/5. Now we have enough information to determine a parametric set of equations of the line of intersection between both planes. Remember, the vector parallel to both planes, let's see where that vector is. That vector parallel to both planes has components -5, 7, and 11. Let's put that here. -5, 7, and 11. The parametric set of equations are given by x equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct. Well, this then is just x equals x0 is 0. I'll just write it out here, but this is redundant. Plus a, well, a is -5, t. For y, we have y equals y0. Y0 is 9/5 plus bt, so that's plus 7t. And for z, we have z equals z0. Z0 is 7/5 plus ct plus 11t. So to write this all out now, we have a parametric set of equations for the plane given by x equals -5t, y is equal to 9/5 plus 7t, and z is equal to 7/5 fifths plus 11t.